All right. So our second talk will be given by Mike Hermele. Take it away.
Okay, thanks, Shuheng. Maybe I shouldn't thank the organizers, but I would like to thank my co-organizers. And also, I definitely would like to thank the Simons Foundation, and everyone who's here who's been participating in the UQM collaboration. It's been great to be a part of it for 4 years, and I think the collaboration has inspired a lot of really exciting discussions and some great work that wouldn't have happened otherwise. So I'm really excited to tell you about this work today, partly because this concerns some issues where my perspective actually changed a lot over the last year. Okay, and to set the stage for this, I think we would all agree that there's been huge progress over the last, let's say, 15 years understanding gap phases of quantum many-body systems at some level of generality. But I want to ask a question. How do we define gap phases? And at some level, it might seem like a silly question. In Shia and Tim's very nice talks earlier today, the definition of gap phases was mentioned almost in passing on the way to something more interesting early on in the talk. So maybe a silly question. On the other hand, there are a lot of mathematicians who would tell you that it's not a silly question and the answer is no. Okay. Although I'm not aiming for a mathematically precise definition here at all, I actually think that this is a much trickier and subtler question than I used to appreciate, and that I think most of us in physics appreciate. And I think it needs actually quite a bit more attention. And the thing that got me to think about this is recent work on fracton systems, which I'll review, that suggests that this question may be quite tricky. And what I want to do in this talk is sketch a single definition of gap phases that behaves nicely both for fracton systems and topological phases. And I would say that I used to believe this was not possible, and I think that was the consensus in the field. So there are important consequences, I think, for fracton physics, and I think there's a good chance that this could be useful more generally. And as I said, I'm not aiming for mathematical precision. So just a very quick review, what are fracton systems? So these are, many-body quantum systems, zero temperature, equilibrium, that have gapped excitations of restricted mobility. So for example, this is a point-like excitation. It can happen that there's no local process where you can destroy this excitation and move it over here. So no string-like operator that destroys this excitation and moves it over somewhere else. But you might be able to destroy this operator and create it here if you also create some other excitations. It has a consequence that if you have an isolated such excitation, it will be immobile, but these excitations can be mobile in some more cooperative way in groups. Okay, and you can also have other kinds of excitations of restricted mobility. You can have excitations restricted to lines or planes. Just to mention one example, which I think is probably the simplest example, this is called the X-cube fracton model. Qubits live on the links of a 3D cubic lattice. It's very much like the toric code. The Hamiltonian is a sum of commuting terms that are products of Pauli operators. It has fracton, line-on, and plane-on excitations. I won't go into any more details about this model. I'll mention that there's a similar model called Haas cubic code, where the non-trivial excitations are all fractons. Okay, that model was discovered first, but I think it's in a lot of ways more complicated, still much less understood. And by now, there's really a vast landscape of examples, of which this is just one, and we have very little understanding of that landscape overall, I would say. Okay, so why is this an interesting subject to think about? Well, the reason that I find this particularly interesting is that I think fracton phases really present challenges for our usual ideas about universality in quantum condensed matter. And what I mean by that is there's a kind of conventional situation which encompasses a lot of what we might still call exotic phases, where we have a system, it's in some phase, which has universal properties, and via the renormalization group, which relates physics at different scales, it's linked to some kind of effective continuum quantum field theory description. Okay, so this is a story that plays out over and over again in many different settings. It's extremely powerful. It underlies a lot of how we think about condensed matter systems. So in fractons, I think at this point, it's fair to say that we know that we need major changes in how we think about both RG and effective quantum field theories. Okay, and we've made some progress in both those directions, but I think that story is far from over. There's also been a belief, I believed this a year ago, I think it was also kind of the consensus in the field, that we need major and system-dependent changes in how we define phases. Okay, so I'm saying, you know, RG has to change, this has to change. We've believed that we also have to make big changes in how we even define phases when we think about fractons. And those changes actually are different depending on what fracton model we're thinking about. That's been the belief. Okay, I no longer think that's true. So what I want to try to convince you now is that it's actually enough to make a mild and system-independent change to what I'll call, in some quotes, a standard definition of gap phases. Okay, so I want to try to sketch this definition. So first I need to, you know, quantum phases should be some equivalence classes on a set, or maybe a space, of quantum systems. So first we need a definition of what we mean by a quantum system. Okay, for simplicity, I'll focus on bosonic quantum systems on a lattice in d spatial dimensions, and I won't impose any symmetries. And on the sites of, I'll always consider the hypercubic lattice in d dimensions, and on each site I'll put some finite dimensional Hilbert space. So this is some picture of that in 1D. We can have these two different Hilbert spaces here, H1 and H2. We're allowed to have empty sites where we put a one-dimensional Hilbert space, no degrees of freedom there. For simplicity, I will always work in infinite space. I think there are a lot of advantages to this. We can also talk about infinite sequences of finite systems, but I won't take that perspective. Okay, it should be possible to translate statements into that perspective. There's a Hamiltonian, which is finite range, and its energy spectrum is gapped, because we want to talk about gap phases. Now, something I'll come back to later, but I think is very important, is that we need some kind of a spatial homogeneity condition to avoid pathological behavior. Okay, but more on that later. Okay, so quote-unquote standard phases are some kind of equivalence classes on quantum systems, and I want to think of this equivalence relation as generated by a finite sequence of moves. And what are the moves? Well, the Hamiltonian depends on some parameters. We're allowed to change them continuously so long as we keep the gap open, don't pass through first-order phase transitions, and so on. So that's kind of the essence of what we mean by phases, continuous deformation of the Hamiltonian. There's another operation that from a lot of experience with topological phases we know is important. We want to think about product states as a free resource and allow ourselves to stack with them. So take the ground state, take a tensor product with a product state. Okay, and there's a corresponding operation you can do on the Hamiltonian. Okay, it's often thought that this stacking operation is there to get a nice answer, if you like, for mathematical convenience, but it actually has a physical justification, and I'll come back to that later. That will be related to some other points that I want to make. Okay, so the idea is that any two systems related by a finite sequence of these moves and inverse moves are equivalent. That's an equivalence relation. Okay, so now I want to spend a minute talking about two nice properties that I think we want phases to have. And these properties both have to do with the renormalization group. Okay, so one property is that within each gap phase, there should be an RG fixed point, where if we keep running the RG for a long time, maybe infinitely long, we'll eventually flow to that fixed point. And the intuition here is that if we run the RG forever, the correlation length will go to 0, and at that point there should be some kind of scale-free description, which is the fixed point. In general, this fixed point you might need to use a quantum field theory to describe the fixed point. It might not really be a lattice model. Okay, but we believe there should be something like that, or at least we would like that to be true. One point I want to emphasize is that sometimes we talk about phases as fixed points, almost like the definition, phases are defined by different RG fixed points. I don't think that's the right point of view. I think it's a property. So I think phases should be defined as an equivalence relation, and then you want that equivalence relation to have this property. Okay. Okay. Yeah.
Do you want to have a unique RG fixed point, or at least one?
Yeah, uniqueness is an interesting question. I would just say at least one. Yeah, I don't want to make any claim about uniqueness. I'm not sure about that. Yeah, good question. Okay, another property that I think is important, and without which this picture that I drew doesn't really make sense, is what I'll call scale independence. And this is just the property that if you run one step of the RG, so you rescale some finite amount, that RG step maps the system back into the same phase. So RG operations keep you within the same phase. And the intuition behind this is that if you run one step of the RG, you start with a system, and then you get an effective description valid at longer scales. And those two models should really be in the same phase. Okay, some system and then effective description of the same system. They shouldn't be in different phases. That somehow doesn't quite make sense. Okay, so now let me sort of show you how this works in the context. Oh, and there's one other thing I wanted to say, so that, I said that the fixed point might not even be a lattice model, but there are, in some phases, there are certain special lattice models, like the toric code, where the correlation length is just 0 exactly at the beginning, and then the lattice model itself can be an RG fixed point, okay? And I'll be concerned with those kind of examples in this talk. Okay? And in that sort of situation, there's a set of ideas that we call entanglement RG, which I'll kind of summarize. So imagine that we start with very schematically, start with the 2D toric code on a square lattice. I'll keep track of the lattice constant, which I'll call A, but this is supposed to be infinite 2D space. And the first thing we do is we apply a local unitary, so finite depth quantum circuit, and we get a new system, which consists of two parts, which are decoupled. So a toric code with twice the lattice constant, these purple dots, and then these blue dots are now qubits that are in a product state, and they've become decoupled from the rest of the system. Okay? And then the next step is that we just integrate out the decoupled qubits. Okay, and then we get the toric code at twice the lattice constant. If we want, we can then rescale space and get back to where we started. That shows us that we have a fixed point. But you don't need to do that. You can just say, look, now I have my effective description that's valid at longer scales, and you can keep going if you want. Okay, so the thing to observe here is that both of these RG operations are phase equivalence moves in this standard definition of phases, right? This is the same thing basically as a continuous deformation of the Hamiltonian. This is unstacking with product states, which is allowed. Okay, and so that tells us that the toric code phase is scale independent, as we would like. So that's nice. Okay, but what about the X-cube model that I told you about? Okay, so what happens if you try to do entanglement RG there? Here I'm telling you about the work of these authors. Wilbur, Shirley, and Xie Chen are here in the audience, of course. So let's start with the X-cube model at lattice constant A. Apply a finite depth circuit. We can turn this X-cube model into an X-cube model at twice the lattice constant, stacked with a bunch of toric code layers, many toric code layers, perpendicular to all three principal directions of the cubic lattice. Okay, so let's try to turn this into an RG. So this is the first step. Okay, this kind of looks like what we did for toric code, except we don't have a product state here. But if we want to have a hope of making the X-cube model into a fixed point, we need to integrate out the toric code stacks at this step. So we integrate out the toric code layers. Now, there are a couple of things we can say about that. One thing we can say is this is definitely not a phase equivalence move. We're not allowed to do that. Okay. Another thing we can say is from the point of view of RG, this is a very exotic and unconventional thing to do because we're integrating out some layers which are described by a non-trivial TQFT. And depending on global properties of space, if we play around with that, there can be low energy degrees of freedom associated with these layers. It's not the sort of thing we're normally allowed to integrate out when we do RG, but we're going to do it anyway. And you might think about this as something, if you feel uncomfortable about that, I think that's reasonable, but maybe it's better to think about this as somehow, you know, this is beyond RG. It's like RG star or something. Okay. All right. Okay, so it turns out, you know, this is not a phase equivalence move. You can actually show that this x cubed model at lattice constant A and x cubed model at lattice constant 2A are not in the same standard phase. I don't want to give you that argument, and the argument, by the way, I think is not that the ground state degeneracy is different, which is, you have to be very careful about using ground state degeneracy. There's a better argument, and I'll tell you about it. If you're interested in it, I'll tell you about the argument later. It will take us a little bit off track, okay? But it's true that these two models are in different standard phases, and so the standard x cubed phase is scale dependent, which is not, you know, that's a property that we would not like to have. And so there's a fix that these people came up with, which is to add a new phase equivalence move. Let's treat these 2D layers as a free resource, okay, and allow ourselves to stack with them. Then this step is explicitly a phase equivalence move, and yeah, Zhuheng.
Just a super quick question. So you don't want to talk about ground state degeneracy. Is it because we are on an infinite lattice? So
that's not the only reason. The main reason, the more important reason, is that ground state degeneracy really relies on boundary conditions. It's not just a bulk property, and so you have to specify more data, and I want to stay away from that. Okay. So we get a new kind of equivalence relation when we do this. It's much coarser than standard phases. The equivalence classes are bigger. And these are what we call foliated fracton phases. And for the x cubed model, these are manifestly scale independent. Okay. There's a very similar story for Haas code, okay, which I won't go through in much detail. Instead of toric code layers, we get something called model B, which is another fracton model whose properties are actually very similar to Haas code, at least roughly speaking. And we expect, although I don't have an argument that I would say that I've written down in full precision, that these two models are also in different standard phases. But it's possible to restore scale independence by adding stacking with model B as a new move, although this seems a bit ad hoc, and I think it's kind of hard to justify, partly because, you know, we want to understand Haas code. We're going to try to understand it by treating model B as something trivial, but model B and Haas code are the same kind of thing. And so that always made me a bit uncomfortable. Okay. All right. So to kind of summarize this, right, you know, this is kind of the understanding for me, let's say a year ago. It seems that if we want these two nice properties of fixed points and scale independence, we need a different definition of phase for topological phases for the x cubed model for Haas code and probably others for other fracton models. And this is definitely coarser than standard phase equivalence. So it's definitely kind of unpleasant that we have multiple definitions. We might hope that there might be just a single definition of gap phase. That would be great. This is also rather far from our basic intuition for phases, right, as just regions in a phase diagram. And so, you know, a question is, do we have to live with this? Maybe this is a fundamental consequence of fractons being weird, and we just simply have to live with it if we want to think about fractons. But I think the answer is that we don't. I used to think that the answer was that we do. And an observation is that in some sense the source of the problem here, if you want to call it a problem, is that two systems that are only different by their choice of lattice constant can be in different phases. That's kind of what led to this situation. Okay. Zhuheng, how am I doing on time?
10 more minutes.
Okay, great. Thanks. Okay. So the approach that I want to take is to go back to the definition of standard phases And I want to modify it by adding more phase equivalence moves, but I don't want to do this in a way that depends on the system I'm considering. Instead, I want to appeal to something which I'll call the continuum approximation principle, which I think is an important idea underlying lattice models that it's good for us to remember. I think we all know this, but maybe we forget it sometimes when we get really focused on lattice models. So anytime we think about a lattice model, really, it's an approximation and an idealization of some underlying continuum system. Okay, so that's the principle. So we should always remember that when we think about lattice models. That doesn't mean that we have to go back to a continuum description, but we should remember that we're making some approximations and idealizations when we work on the lattice. And so we can get a lot of mileage out of this. One thing we can do with this is we can actually give a physical justification for why it's okay to stack with product states. The thing you should think about, is think about modeling a solid where we're very used to the fact that we might ignore some, filled atomic shells or core levels, right? We can choose to include those core levels in our model or not, and get different lattice models that both approximate the same continuum system, but that choice had better not affect the answer to the question of what phase we're in. It's an arbitrary choice we made in our theoretical description. Okay. And thinking along those lines, you can justify stacking with product states, but there are other things you can do. So another thing you can do is you can say, look, we can tune a parameter and we can continuously deform the lattice constant. I mean, we can really do this in the lab. We can apply pressure. Although pressure changes a lot of other things too, I want to imagine that we do this without changing any parameters in the Hamiltonian. The only thing we do is move lattice sites around. Okay, so here's a picture of a lattice, and the formal setup that I talked about, the lattice sites don't live in continuous space. They sit on discrete points of a lattice. But you can still mock this up, even in that discrete lattice world. So if you start with a lattice that has a bunch of empty sites, imagine you squeeze on it. If you squeeze on it enough, you can get rid of the empty sites and just have filled sites. Okay. And so this will relate a system with lattice constant A to a lattice system, a system with lattice constant 2A. Okay, and we can also get other phase equivalence moves from the same principle. I think some of them are important, but I won't have time to cover them in this talk. Okay, they won't be important for the main story that I'm trying to tell you. So if we add this move, where we're allowed to do uniform rescaling of the lattice constant, I want to call the resulting phases deformable lattice phases, because that's where the idea came from. And let's reconsider the foliated RG for the X-cube model in that light. Here's kind of a diagram of it. So now it's just obvious that x cube of A and x cube of 2A are equivalent as DL phases by this lattice deformation. And so again, the deformable lattice x cube phase is scale independent. Okay? But there's a big difference from foliated fracton phases where toric code stacks themselves are by definition trivial as a foliated fracton phase. A system which is just toric code stacks is definitely non-trivial as a DL phase. And that fits with our intuition a little better about what's trivial and what's non-trivial. Okay, so that's a difference from foliated fracton phases. So this same story goes through in basically the same way for a large class of fracton phases. Maybe I won't go through this in detail. I'll just say that the same statement also applies to Haas code. Ruben, did you have a question?
Quick one. So I guess part of the message here is that these phases are absorbing the other phases?
Yeah, you can think of, right. So for example, you can think of, that's one way to think about this diagram. It's like the X-cube model is something that can, it can eat toric code stacks and get bigger. Yeah. It's sort of a resource theory spin on this. And I think there are interesting questions there that would be good to explore more. We could chat about it later. Yeah. Right. Let's see. Where are we? Oh, I went back too far. Yeah. Okay. Okay, good. So what are the consequences for fracton physics, just to summarize a little bit? Well, so one point is that, I think fracton RG is definitely exotic. I don't think we can really get away from that. But it doesn't have to go together with phases that are exotically defined, like foliated fracton phases. I do want to say that I still think foliated fracton phases might be useful and important, but not because we need them, but because they might help simplify our understanding as a higher level of structure, right? Just to cut down on this massive landscape of different fracton models. And it is true that these rather conventionally defined DL fracton phases, they're still associated with exotic RG fixed points. There's definitely UV-IR mixing. One way to see that is the exotic RG itself. And so there's a lot of, this by no means gets rid of a lot of the weirdness in fracton phases. I think it's still there. Okay. One thing I would say is that this has actually made me a lot more optimistic about the role of continuum field theories as effective theories for fractons. And in particular, I think that this whole story suggests, because ultimately the RG should be the link to the continuum, suggests that the universal properties of these rather conventionally defined phases should be nicely captured by effective field theories. And I think there's more work to be done to understand that, and I'm pretty excited about that. So the last thing I want to comment on in just a minute or two, I won't say everything about this, is come back to this condition of spatial homogeneity. So why is it important? Why do we need that? Well, what about this system? In 2D, we can have a gapped interface between a trivial product state and toric code. This is a completely legitimate gapped state, but what phase should this be assigned to? There's no answer to that question, I think. The answer to that, the right reaction to this is we shouldn't be asking this question. We need to find a way to not ask the question. So one way to not ask the question is to impose some restriction on states we're allowed to consider so we never have to think about this state, right? We want spatially homogeneous states. So there's an easy way to not do this. It works, but it's not the way to do it, which is to impose translation symmetry. That makes things homogeneous, but there's a problem that comes with this, that we get a lot of extra phase invariance associated with the translation symmetry itself. For example, to mention some recent work of Xiang, Song, and Senthil, if we take 2D topological order of the toric code, with translation symmetry, there are 12 different phases in the presence of translation. They all become the same phase if you break translation symmetry. And we would really like to be able to think about that underlying phase without any symmetry first. And then if we want, we can add symmetry later. Okay. So there's a compromise, which I think is a useful compromise. It actually came from thinking about fractons. Maybe I won't have time to explain that. But the compromise is to say, let's allow some limited breaking of translation symmetry, where we enlarge our unit cell only by some finite amount, arbitrary but finite amount. So the idea, quickly, is to modify this definition of DL phases by restricting to systems with some translation symmetry, with some unit cell. There's not a fixed unit cell. And then go from there. And so what that means is that the individual systems you consider always have some translation symmetry, but you can consider deformations where you're allowed to enlarge the unit cell and break the symmetry. And you can make an argument that if you do this, at least for 2D topologically ordered phases, those described by unitary modular tensor categories, you can make an argument that this gets rid of all of the extra phase invariance associated with translation symmetry. So this is kind of a nice property. Zhiheng.
What about just taking decoupled stack of 2D toric code in 3D? That's translation invariant in some direction. Is that trivial or non-trivial?
Decoupled stack of
2D toric code layers.
Yeah. So there. Well, I don't think that should be trivial, because I don't think there's any way to deform that to a trivial state. Even if you break, even if you break symmetry completely, I don't see how to deform that to a product state. There, what I would say, right, so there's still this keep. So what this coarse translation does, which is important in fracton phases, is it lets you talk about the mobility of these restricted mobility excitations at large distances. And so the idea is that this mobility over large distance is an important property of fracton phases, including this decoupled stack of toric codes, because the idea is that if you translate your excitation up perpendicular to the stack direction, you get a different kind of excitation. So doing that by 1 unit cell, 2 unit cells is maybe not very important, but it at long distances, that property, the intuition is that somehow should be important. So this way of defining phases, it keeps track of properties like that. So it keeps long distance mobility. And I think there's more thinking to do about like whether you really want to keep track of those properties or not. I think there are big advantages for thinking about fracton phases and characterizing them in terms of their gapped excitations. I think, yeah, I mean, I don't have a lot more to say about that. I think there are interesting questions in that direction. So I think I'm out of time, so I'm going to skip this and just go to some outlook. So I think the maybe biggest takeaway for me is that, I said, I used to think that I pretty much knew how to define what phases were, maybe not in a mathematically precise way, but precise enough for me. But I actually, even after this work, now I feel much more uncertain about that, which I find kind of interesting. And I think that we really need more careful thinking from a variety of different points of view about how to define phases and what definitions are going to get us what we want. From physics perspectives, also from mathematics perspectives. Okay. And the other thing I would say is that, something I think is quite, I think this is an exciting opportunity where maybe I would have been kind of uncertain about this a year ago. I think it's a great time for more work on thinking about effective field theories for fractons. Definitely we've made a bunch of progress on continuum field theories related to fractons, but where I think there's certainly room to do a lot more is to think carefully about the relationship between those continuum field theories and universal properties of phases. And I'm optimistic that we can do a lot in that direction. And okay, these are perhaps some more. I think these ideas can be applied to other settings. I even know of one application of these ideas to rather conventional invertible phases, which I can explain offline if anybody is interested. And let me stop there. Thanks.
Hi, Mike. Nice talk. I was wondering if there is some maybe connection between taking the lattice constant to 0, and if something goes wrong, then there's something fractonic-y about it.
Yeah, I don't know what it means to take the lattice constant to 0.
Well, you mentioned like you can smoothly deform the lattice constant, right? But
I see. In that sense, yeah. Like so, you kind of okay, right? You're taking this idea. I'm worried that maybe this takes the continuum approximation principle too far, but yeah, I mean, you're kind of asking what happens when we deform so that all the degrees of freedom kind of pile up, basically, and the lattice constant really goes. I mean, then I guess, I mean, then you get a system which has some infinite number of degrees of freedom per unit volume, right? Which maybe it's okay, but I don't.
Like a field theory would have that, for example, right?
A field theory would have that. I guess my point of view is I want to stay away from that. Like I want to insist that the number of degrees of freedom per unit volume is always finite. But I mean, maybe that is useful for connecting with field theories. Yeah, but I haven't tried to think about it.
Thank you for the talk. I guess I have maybe the dual of that previous question,
Okay.
where so from continuum approximation principle, by definition, you can change the lattice constant and you still belong in the same phase, right?
Yeah.
I'm a bit confused about what the implication of that is, because naively then it looks like any point is a fixed point of RG, but where I can do the continuum approximation principle to expand the lattice constant and then shrink it by claiming that RG was just coarse graining, but there's no degree of freedom. So you just go back to the original lattice constant and you can continue this loop.
That's a great question. So that's not really RG because you're not integrating anything out. So the most important thing in RG is that you integrate out at some point, right? Suppose you can do RG without ever rescaling space. In fact, rescaling space is sort of, it's like you should think of it as something optional that you can do at the end to check whether you are getting closer to a fixed point or not. If you don't care about fixed points, if you just want to flow, you never need to rescale space. The non-optional thing is to integrate some things out. And if you did what you were suggesting, that doesn't involve integrating anything out, so it's not, you have to reduce the number of degrees of freedom per unit volume in an extensive way, I think, for something to be considered RG. So I don't think, so I guess my reaction would be to say, like, that's not, like, that wouldn't count as RG. Right? The other thing I would say is that it's important to make a distinction between phase equivalence moves and RG operations. They're not the same thing, right? Like, you can, just because something is a phase equivalence move, that doesn't mean that you want to allow it as an RG operation, and vice versa.
Okay, thanks.
So the way you're solving the problem about fractons is that you're giving up a property of the set of phases that I didn't realize I was assuming, which is that if you tensor with something and that's equal to something, then the thing you started with is nothing.
Can you say that again?
So although a stack of toric codes is not trivial,
right?
If you tensor a fracton x cube model with a stack of toric codes, it's the same as the x cube model.
Right. Yeah. It's related to the question Ruben asked.
Right.
Yeah.
Right. So
yeah.
So this is some property of the set of phases that it's not that it's not a group. It's definitely not a group, but it's some property of, like, some multiplicative property.
Yeah. There is some interesting. Yeah. There is some interesting. Right. There are certain kinds of phases that can kind of eat other phases and destroy them. Yeah. Yeah. And somehow that's important in all of these exotic RGs. Yeah.
Well, if there's no more questions, let's thank Mike for a stimulating talk. The thing that's being eaten is non-trivial, but basically it's eaten.
Right. In isolation, it's non-trivial.